Welcome back to Chemical Process Safety. In this video, I'll talk about fault trees and event trees, which are two separate but analogous ways for quantitative risk analysis. The difference between these two are the types of logic, deductive versus inductive reasoning. A fault tree starts with the consequence of the event, and then it works backwards to determine the events that contributed to the consequence. In contrast, the event tree starts with an initiating event first, and then it works forwards to identify the safety functions that are designed to deal with the event, and then it'll assign probability for either failure or success of these safety functions. And at the end, those probabilities can be multiplied together. I think this explanation is okay, but it's difficult to see without looking at an example. So I think the best thing to do is start by considering an example. So let's say we had a reactor, and that reactor had two parallel systems on it that would be designed to prevent overpressuring of the reactor. The first one would be a pressure indicating alarm, or PIA, and this would hopefully identify operators or people in the control room that there was a high pressure event going on. So this PIA is attached to an alarm, and that alarm is what sounds, or the alarm would go off, and that would alert people to manually initiate depressurizing of the reactor, either by some kind of cooling water mechanism to quench the reaction, or opening of a relief valve or something like that. The second system is PIC, Pressure Indicator Controller. And here what we're doing is we are attaching this to a solenoid valve, and the solenoid valve would open. Presumably there's cooling water in this pipeline that would do the same thing, that would quench the reaction very rapidly in the event of a high pressure system. So let's start with a fault tree first, and we'll start with the consequence of that. So the consequence of everything failing is an overpressuring of the reactor. I tend to like the event trees a little bit better because I get to use the logic. I like use of the logical operators to think through these a little bit better. It makes a little bit better sense to me. Okay, so in order for the overpressuring of the reactor to occur, this is the first thing you would write down. You'd have to think what events would contribute to that. So if I break down the two subsystems separately, because they're connected in parallel, I could call the pressure indicator alarm one subsystem, and the pressure indicator control connected to the solenoid valve another subsystem. So if the reactor were to overpressure and rupture and explode, it would require both of these systems to fail. And whenever I use the words both, parallel, these are all indicators that an AND gate would be the thing to consider. So in other words, if the overpressuring of the reactor were to occur, it would require this system to fail and this system to fail. And the use of the word and is what leads me to use an AND gate for this bit of logical structure. All right, so now we've got two things that go into our AND gate. We've got a failure of the alert system, so that's the left side, and a failure of the automatics system, that's the right side. So if we break it down one step further, there's two components that go into the alert system. There is the pressure indicator, and there's an alarm. So in this subsystem, so just considering these two things, if the pressure indicator fails, then again, the alarm is not going to know that it's supposed to trigger. And in contrast, if the pressure indicator works, but the alarm doesn't, then the ending point is still the same. The alarm doesn't go off, and this entire system fails. So these two pieces of instrumentation should be connected with an OR gate, designated again by this Pac-Man icon. I'm also labeling them with A, B, and C. These are completely arbitrary names or letters. They don't mean anything. It's just going to help me to keep things organized when I write equations. So in the book, I don't have the mu value that I have is for a pressure switch. So I know it's pressure indicator. Pressure indicator is not on the table, but pressure switch is the same thing. Similarly, I don't think alarm is on there. I think it's written as an indicator light, but that would be what the alarm would be. All right, so that's the left side. If I now consider the right side, I've got a very similar logical structure going on. So if this pressure indicator fails, then obviously the solenoid valve isn't going to know that it's supposed to engage. And in contrast, if the pressure indicator works, but the solenoid valve does not, then I still get to the same point of overall failure of the system. So this branch is also connected by an OR gate. Also in event trees, the convention is to have the basic events be circles and the intermediate events be rectangles. So once you get down to the basic component, or the thing that you would actually look up a mu value for, you put it in a circle. And then you connect things with logical structures, each going into AND gates or OR gates as appropriate. Now, all the stuff in red is just math that I've pre-done before. I'll walk you through or step you through how to do that math. What you would do is you would look up the mu value in the table in the book, and you would calculate the reliability based on that mu value. So remember that reliability is equal to e to the minus mu times t. And for this type of analysis, we will assume a value of 1 year always, unless stated otherwise. So we calculate the reliability for each one of those components. Just as an aside, notice how the pressure switches have the same exact reliability because they're the same exact mu value. Again, that's an approximation because they may not be identical pieces of instrumentation in real life. It's just the best that we can do with the table, with the data that we have. Also note that the indicator light is a highly reliable piece of equipment, while the solenoid valve is considerably less reliable. So I'm comparing 87% to 96% for the indicator light to 66% for the solenoid valve. And that reflects the complexity of the pieces of instrumentation. So a solenoid valve is a more complex piece of equipment, and therefore it's less reliable. Okay, then what I can do is, if desired, if I have to, and you probably should do this anyway, just in case, but calculate the probability of failure by taking 100% minus the reliability. So these two things are adding up to 1. Every probability of failure plus the reliability adds up to 1. And then based on the logic of the gate, the AND gate versus the OR gate, that is going to tell you whether or not you should multiply the reliabilities or the probabilities of failure. So think of whatever mnemonic that helps you to think about it. I personally like to remember that the AND gates multiplies the probabilities of failure. And I think that way makes most sense to me because, again, I like to think about dice or other types of probability games where the probability of an event, if it's an AND gate, you have to multiply those. And then I remember that OR is the opposite. So in an OR gate, I'm multiplying the reliabilities for the reasons that I talked about in the last video. So again, for the OR gate, I'm multiplying the reliability of this overall system is equal to the reliability of these two things multiplied together, which is 83% or 84% if I round up. Notice that, again, for an OR gate, the reliability of the entire system is less than the reliability for either one of the individual parts. I'll do a similar thing on the other side. The reliability of this entire system is equal to the reliability of the pressure switch times the reliability of the solenoid valve. Here I get 57%, which is a much lower value because the solenoid valve is much lower. So similarly to how I calculated the probability of failure given the reliability here, I'm also going to do the reverse. I'm going to calculate the probability of failure by subtracting the reliability from 1. And that's helpful because the AND gate requires me to calculate the probabilities of failure by multiplying these two things together. So again, PB is 1 minus RB, or 16.5%. PC is 1 minus 0.57, or 0.43. So I multiply those two things together, I get an overall probability of failure for the entire system as 7%. Therefore, I can conclude that the reliability of the entire system is about 93%. Now, I can improve this if that's deemed to be unacceptable by adding another thing, hopefully in parallel so that it's an AND gate. But you can also think about maybe substituting instrumentation using more reliable things that have a reliability higher than 66%. Those are both ways that you could improve upon this. Let's switch gears now and talk about the second type of tree, which is the event tree. So this one is the one that works forwards, and some people like this way of thinking about it better. So for the same exact scenario, let's say that we've got a high pressure event occurring in the reactor. So not necessarily the reactor is overpressured, but it has the potential to have an overpressure. And the way that these things go is the events are written across the top with failures on demand written below. So for this, I'm not necessarily using the table. These were given to me by the problem statement, or I made them up. But these failures on demand would be given to you. So what this means is for every 10 times that the situation would arise that I would require the high pressure alarm to alert the operator, I would assume that like one time out of those 10 times, I would have a failure of this particular system. So the first line of defense would be the high pressure alarm would be alerting the operator. And also for this analysis, we'll take out the possibility for human error. So we'll assume that the operator is indeed alert, is not asleep on the job or anything like that, or tired or misses the alarm. We'll assume that the alarm is actually a thing that's not working. So basically the way it works is that the event is either successful, in which case the branch goes up, or it's unsuccessful, in which case the branch goes down. And then we just keep adding branches as the events go. So let's explore the top branch first, the successful branch. If the high pressure alarm alerts the operator would then have to shut off the feed to the reactor. So again, successful is up here, and we'll assume that this failure on demand is much better. So every 100 times the operator needs to shut off the feed, we'll assume that they do it one time or 99 times out of that 100, or they fail to do that one time out of the 100. So successful is up here, and if that is successful, right, if the feed is shut off, then the reactor is shut down successfully. If the operator does not shut off the feed, I have an unsuccessful branch, and that is going to lead to a runaway reaction and an explosion. The other branch to the logic is unsuccessful, a high pressure alarm alerting the operator. And in that case, I'll have the possibility for pressure sensor 2 to engage the solenoid valve and shut down the feed that way. So again, success is up here, failure is down there. In this branch, I have a reactor shutdown if the pressure sensor engages the solenoid successfully and shuts off the feed. And in this case, I have a runaway reaction where both things have failed. And then to work out the probability, all I have to do is multiply probabilities along that way. So for the case of this there's 4 possible events, and then 2 of them are the same in both instances. But if I want to work out the probability that my path follows this top branch, I would multiply these probabilities. So again, this is failure. So I maybe should have started with the bottom so it was clearer, but successes are 1 minus the failure rate. So here I have 90% of success. Here I have 99% of success. So in order to calculate the entire probability, I'm multiplying these. This should actually be, I made a mistake here. This should be 1 minus 0.10. I think I got confused because I wanted to write 90% here and I ended up writing 1 minus 90% instead. So again, here it should be, let me just erase this briefly. All right, cool, I fixed it. So the probability of this branch would be 90% times 99%. So this one's going to be probably the most likely. For this branch of the runaway reaction, I have to have a successful high pressure alarm alerting the operator, and then an unsuccessful operator shutting off the feed. So this branch is 90% multiplied by 0.01%. So that's going to be considerably less because that's a much less number. This branch, just keeping on for completion's sake, this one I have a 10% chance of going to the unsuccessful branch, and then a 98% chance of going to the successful branch. And this one is 10% and 0.02%, 0.02 or 2%. So after I calculate all these numbers, if I were interested in the total likelihood of the runaway, remember I have 2 scenarios in which I have a runaway reaction, I would simply add the probabilities for these 2 occurrences. Similarly, for the reactor shutdown, I would add the probability of those reactor shutdowns. And then as a final check, I would just see that the total of all my outcomes is equal to 1. So I'm going to wrap that video up here. Hopefully you enjoyed. As always, see you next time.